element that belongs to A intersection B, but that does not belong to A intersection B. We are interested in element that does not belong to A and B, that does not belong to A intersection B. That gives us the shaded portion. That is, the shaded portion here, we are interested in elements that does not belong to A intersection B. Then we have S, the picture that actually deals with S, M, and P. Here it is M intersection S intersection P complement. That is, we are not interested in P at all, but we are interested in elements that belong to S and M, that is, that belongs to both S and M. S and M will give us the middle portion where S and M overlap, but does not belong to P. That is, it belongs to the whole of M and partly S. That is, element common to both S and M. That gives us the middle portion, but we are now subtracting the whole of P completely out, and that gives us the shaded portion. Now, for the next one is A union B, A union B union C. That is, elements that belong to B and C, and also after we combine B and C together, also belong to A. That gives us all the three sets being shaded, which is also complementary to A union B into brackets union C. Then the next one is P intersection Q, P complements intersection Q intersection R. That is, here when we say P complement, that is, all the elements we are interested in are not in P, but are in Q and R. That is, belongs to both Q and R. That means the element of interest belongs to both Q and R, are common to both Q and R, but not in P. And that's the portion being shaded. Then we now have elements P intersection Q intersection R. That is, elements that can be found in P, that can be found in Q, and can be found in R. And that is the portion at the middle, that is where the three circles overlap, where the three sets overlap. Now we'll now go to the examples and then solve some examples. Example number 1. If Q is equal to all sets squares, all perfect squares less than 30, and P is equal to all odd numbers from 1 to 10, find Q intersection P. That is, elements that can be found in P and Q that are common to both P and Q. Here we are not interested in elements that are in Q but are not in P, or elements in P that are not in Q. But our point of interest is the elements that are common to both P and Q, elements that can be found in P and Q. Now, the first thing we have to do is we are going to list the elements in Q. But mind you, the type of bracket we are going to use is not that common bracket, but this type of parenthesis. Now, we said all perfect squares less than 30. 1 is a perfect square. Then we have 4. That's 2 times 2. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 15. Is 25. And then 6 times 6 is 36, but we said less than 30. So these are Q. Then P. They said all odd numbers from 1 to 10. That is, it's a finite set. It's a finite set. Now, that will be all odd numbers. That will be starting from 1, 3, 5, 7, 9. These are the elements in P and then Q. Now, P intersection Q, that is elements that can be found in P and also can be found in Q. That's the meaning of intersection. So, which element can we find in both P and Q? One, we can find one in Q and we can find one in P. That is, we can find one in P, we can find one in Q. So that will be, now, if you have to list the elements in P intersection Q, we have 1. We can find 3 in P, but we can't find 3 in Q. So it's not part of it. We can find 4 in Q, but not in P. We can find 5 in P, but not in Q. But we can find 9 in P and also in Q. So we have 1, 9. Now, let's still check. Out of 7, we can find 7 in P, but not in Q. Then 16, can we find 16 in P? No. Can we find 25 in P? No. That means for our answer, P intersection Q is equal to 1 and 9. That is, the elements of set P intersection Q is 1, 9. Example number 2. Use the information below to answer questions 2A and B. Our set U is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Set P is equal to 2, 4, 8. That is multiples of 2. While set Q is equal to 3, 6, 9. That is multiples of 3. And R is equal to 1, 5, 7, and 10. Now, for our question example number 2A, they said we should find P complement intersection Q complement. Then B, R complement intersection P. A is P complement intersection Q complement. Then B, which we are to find, is R complement intersection P. Now, for us to know, these are universal sets. Now, for us to know our P complement, the first thing we have to do is to know our P complement, which is equal to, that is, elements that does not belong to P but are in the universal set. Now we have 1, 3, 5, 6, 7, 9, and 10. We are having 3 elements here, we are having 10 elements here. That means we must have 7 elements here. 1, 2, 3, 4, 5, 6, 7. Now, Q complements. That is, elements that can be found in our universal set but not in Q, which is equal to that 1, 2, we have 3 there, that will be 4, 4, 5, 7, 8, 10. Here also we are having 3 elements in Q. That means we must have 7 elements that does not belong to Q but belongs to a universal set. 1, 2, 3, 4, 5, 6, 7. Now we are now interested in P complement intersection Q complement. That is, elements that belong to both P complement and then Q complement. Which elements belong to both? We'll try and see that now. 1 belongs to both. After 1, 5 belongs to both. 5 belongs to both. 7 and then 10. Then for our B, That's R complement intersection P. That is elements that belongs to P and also to R complement. We'll be given P, but we don't know R complement. Now these are elements in R. So what would be needful for us to check for elements that does not belong to R. That will be R complement, which is equal to 1 is in R, 2 is not there. That is, we are dealing with elements that are not in R, but are in the universal set. 2 is not in R, 3 is not in R, 4 is not in R, 6 is not in R, 8 is not in R, and 10 is not in R. Here, we are having 4 elements that belong to R, which means there are 6 elements that does not belong to R. So that's 1, 2, 3, 4, 5, 6. That's the cardinality of R complement. Now, we are now interested in R complement intersection P. Now, R complement intersection P, which is equal to 2 can be found in both, 4 can be found in both, and 8 can be found in both. So we can easily say that P is a subset of R